In my last video, I showed you what happens when an AI agent reads a malicious web page. The agent licked its own system prompt. There were no errors, no warnings, it just complied. That video was the problem, and this one's the solution. In this video, I'll show you 5 layers of defense. But before we get into the code, you need to understand why this is a fundamentally different security problem. Now, in traditional security, you secure at the perimeter, you validate at the edge. Everything inside the wall is trusted. In agentic AI systems, everything the agent reads is the attack surface. Every retrieval, every tool response, every document. The agent can't tell the difference between data it's supposed to process and instructions it's supposed to follow. That's the root vulnerability, and it's why you need multiple layers, not one clever fix. The very first defense pattern is really the simplest. Here's the agent from my last video. It had just one tool, the fetch web page tool, and that's the one that got exploited. But in production, you'd often see something like this. A research agent with access to email, the file system, a database, because someone gave it access to everything during development and just never bothered to scope it down. The simple fix is if your agent's job is to summarize articles, it really only needs one tool, fetch web page, and that's it. Every single tool you add is another attack surface you're handing over to an attacker. But least privilege goes deeper than just removing tools. The real defense is making the constraint deterministic. You enforce it in a layer that the model can't see and can't argue with. Every major framework gives you a way to do this. LangGraph calls it middleware. OpenAI Agents SDK calls it guardrails. Strands calls it hook events, and Google's ADK calls it tool context. Different names, same architectural point. The model generates the intent, but a deterministic layer outside the model decides whether that intent actually gets to run or not. This is model proof. If the agent tries to execute a drop on a read-only context, it gets a hard error. Now, this doesn't stop the injection attack from my last video. The agent still reads the malicious page, but at least it limits the blast radius. Even if the agent gets compromised, the worst it can do is fetch a web page. It can't email your credentials or write to your database. Least privilege was about limiting what an agent can do. This pattern is about limiting what an agent can read. It's called the dual LLM Sandbox. The idea here is simple. Never let your reasoning model see raw external content directly. Route everything through a sanitizer first. I've set this up as a 3-stage sequential agent pipeline. First, a fetcher that grabs the raw HTML. Then, Gemini 3.1 flashlight, acting as our sanitizer, that processes that HTML. It has no tools and one specific job: to take messy, potentially adversarial content, strip out any instructions, and return only factual data. The final stage is our reasoner, powered by Gemini 3 Flash. It does the actual summarization, but it never gets to see the raw malicious web page, only the clean output from the sanitizer. I'll run this against the same malicious page I had in the last video. And there it is. The same page that compromised the agent before, now we get a clean summary of the article. The hidden instruction got stripped by the sanitizer before the reasoning model ever saw it. I'm piping the traces into Phoenix, and you can see the 3 spans: fetcher, sanitizer, and reasoner. Here's what went into the sanitizer, the full poisoned HTML. You can see the injection block right there, but the reasoner got only the cleaned article. Now, this pattern is real, measurable defense, but it isn't bulletproof either. A clever injection could still fool the sanitizer, which is exactly why you don't stop here. Even with a sanitizer in place, you should never just blindly trust the output of your agent. This pattern adds a checkpoint between what the agent decides to do and what it actually does. Here, I've set up another sequential agent pipeline: planner, validator, and executor. The planner comes up with the actions and what tools are needed based on the user's request. But before those tools are executed, the validator intercepts the plan. This is our security gatekeeper. It doesn't have any tools, only a rubric. It checks for three things: scope, intent, and proportionality. Does this plan stay within the predefined expectations of the user's request? Is the proposed action actually a faithful response to what was asked? And is the risk of this action, like hitting an external API, proportional to a simple request for a summary? This isn't just about catching errors, it's about securing the application by ensuring the agent never hallucinates a high risk action that the user didn't authorize. If any of the validator's checks fail, the plan never reaches the executor. The executor only fires its tools if the plan is approved by the validator. For this demo, I have set up two scenarios. In the first one, the user asks the agent to summarize the page. This is a normal in-scope request. But for the second one, the user asks for the summary and then for the agent to email it to an external address. Two requests, same pipeline. Let's see how the validator handles each one. First, the happy path. I'm asking for a simple summary of my website. It's a normal public web page. If we look at the traces, you can see the planner proposes a simple fetch. The validator sees the request is just for a summary. It confirms that fetching a URL is proportional to that goal, and it approves the request. The executor then proceeds to call the tool, and we get our summary back. Now let's try something different. I'm asking the agent now to summarize a page and email it to an external address. This time, the planner includes send email in the plan because that's what I asked for, but the validator flags the email as out of scope. The verdict comes back, rejected, and because of that logic, the executor never even touches the email tool. The action is blocked before a single packet is sent. Now, the previous patterns are defenses that the system runs on itself, but this one is different. It's about knowing when to stop running things and bring a human back into the room. This is the human in the loop pattern. It's important because no matter how clever your validation is, some actions are simply too high stakes to leave to chance. We use a simple golden rule here. If you'll be uncomfortable explaining to a user why their agent did something without asking them first, that action needs a checkpoint. That means that certain actions should never be fully autonomous. For example, sending external emails, writing to production databases, making payments, or deleting records. These should never execute without an explicit sign off from a person. Another important thing to note, particularly for long running multi agent systems, is that when you have agents talking to each other, they can sometimes get caught in an infinite loop. To stop this, we implement a circuit breaker. Now, the code for this is trivial. You just set a deterministic limit on the number of turns. If your agents exchange more than n messages without reaching a human checkpoint, you kill the task and escalate it. It's not a clever AI fix, but it prevents an injection that starts a chain of tool calls spiraling way past what anyone would have approved. The final pattern is the one that ties every other defense together: observability. You simply can't defend what you can't see. If you've been watching this video, every single trace I've shown you, from the sanitizer stripping the injection to the validator rejecting the exfiltration, that's observability in action. Most tools work the same way, so the tech stack doesn't matter as much as the standard. Here are 4 things worth auditing. First, thought signatures. Don't just log the final output, log the model's internal reasoning. If an agent suddenly starts thinking about system files instead of travel itineraries after reading a document, your logs should catch that semantic shift before the agent takes a harmful action. Second, execution traces. You need to see every tool call, every parameter, and every response. Remember the tool poisoning attack from my last video? It was invisible to the user because the agent successfully returned their order history, but the stolen credentials were hidden inside a tool parameter. Without execution traces, you're basically flying blind. Third, UI escaping. If your agent outputs renders in a browser, you should escape the HTML. Otherwise, an injection could generate HTML that executes in the user session. Finally, tool scanning. Treat unvetted third-party tools with the same suspicion you'll give an unvetted npm package. Before loading any MCP servers, scan its tool descriptions. Look for hidden instructions, suspicious parameter names, or anything that doesn't match the stated function. There are a few open source scanners you can run on your own setup, and some MCP clients are starting to ship static validation as a built-in feature. Pick whichever fits your workflow and run it. It takes a few minutes, and it can catch a poisoned metadata description before it ever hits your agent's context. So those are the 5 patterns: least privilege, the dual LLM sandbox, output validation, human in the loop, and observability. But the truth is that no single one of these is a magic bullet. In security, you don't just build one big wall and call it a day. You build layers. You want to make sure that when one layer fails, the next one is right there to catch it. I've linked a few resources in the description, along with the code for the demos if you want to dive deeper. And if you found this helpful, subscribe, and I'll see you in the next one.